You're listening to Science Coast with Mallory Havens and
Chris White.
And our special guest today, the man, the myth, the legend, Dr. Jason Keleher.
Hello, everybody. I'm really excited to be here with Mallory and Chris. I've seen a lot of their example podcasts, and I guess I'm fortunate to have been asked by such a superior team.
Well, you understand that you're not supposed to watch the podcast. You're supposed to listen to the podcast.
The funny part is the outtakes are the best. I just want to let everybody know if you want to subscribe, you should also subscribe to the outtakes. That would be outstanding.
All right. Anyway, Jason.
If we get a Patreon, we'll let you know.
Hey, Jason, can you tell us what you do here at Lewis University?
Yeah, so I'm the chair of chemistry here at Lewis University, sometimes known as the Department of Magic and Potions, but also I'm actively involved in research on campus, and I think this topic today falls near and dear to some of the stuff that we're working on. So it's really cool to be here today.
Okay, so the topic for today, we're going to continue in with our sustainability series, and today we're going to be talking about forever chemicals. And it's been in the news. It's actually something that a lot of people are worried about. There's potential health impacts associated with these forever chemicals, but they're so useful in our society, and it makes life so nice. I mean, we all actually like them. The problem is that many of the things we like actually have negative impacts, and that's kind of what we're going to talk about today. So,
do you want to first define a forever chemical, just in case somebody listening isn't aware?
They're going to let me do that. Okay, good. So I think that's a common misconception, misnomer, misunderstanding in the literature, is also in just the general news. Forever chemicals are chemicals that don't break down in the environment or in our bodies. Ever.
Thus, forever.
Thus the term forever. The central theme, though, is the fact that they're known as very persistent chemicals. And I think that's an important thing to point out. Persistence or striving leads to their superior properties. So my question for everyone always is, do you like your food to stick to your pan?
No.
So therefore, you are going to use a forever chemical on that pan to create a persistent film that results in things not sticking to your pan.
As opposed to single-use pans?
Or just using cooking oil.
Or just using cooking oil. But even there, I mean, the properties you get from these materials, right, are waterproof properties, non-stick properties, controlling the thermal gradient across the surface, so on and so forth. So people think about them as an efficiency or an improvement to what they do daily, but
they are.
And they are, absolutely. But the term forever means that they do not break down and they persist in the environment.
So I'm not sure you answered the question. What are they?
You want to know the actual chemical structure?
Yeah.
So we can get into it. They are perfluoroalkyl or polyfluoroalkyl substances.
Can you break that down just a little bit?
Very simple. They are carbon and fluorine containing molecules. Not fluoride, but fluorine, right? So very different than fluoride, right? Fluoride we know is good for teeth and things like that. These are fluorine-based and hydrocarbon-based materials. So large polymer chains that provide unique properties, right? The problem is their bonding structures make them very stable, very inert. But if they're stable and inert in the application you're using them for, then they are also not responsive to cleaning or remediation techniques.
But I guess I don't understand. How do you make a film that holds together if they're inert? Because I think of like a noble gas as inert and it doesn't bond with anything. And so you're saying that you have this polymer and it's inert, but it sticks together.
Mm-hmm. So the bonding structure is arranged in a covalent network, and that covalent network that's designed has functionality that upon assembly, the macro system creates greater stability. So it's like a harmony or a synergy.
So the individual molecules are kind of linking together
100%
to make a much larger macroscopic structure, which holds together well and for a very long period of time.
Yep. And even if that macrostructure breaks down, you still have the individual chemicals that are what we would call the monomer unit or the small subunit that still are persistent as well. So you have macro, micro, and then all of a sudden you try to degrade everything, it keeps a scaffolding effect and they persist.
And PFAS,
Yep.
yeah, are strongly associated with cancers and other health conditions. Personally, where I grew up, a shoe factory contaminated all of the water supply with these. And so my sister and I refer to it as our future shoe cancer because I'm sure we're both full of them, having grown up on the dinosaur pee water. Well,
Previous episode, everybody.
Well, the PFOAs and PFAS are also in a lot of food packaging, and more specifically what they call food contact packaging, so things that are directly in contact with your food as well.
And theoretically, they're not supposed to come off of the container.
Theoretically.
But not in actuality.
I mean, there's studies showing both, I think, at this point, right?
So it's a trade-off. What we're saying is that there are these chemicals which are incredibly useful and convenient. Maybe convenient is a better word for it. It makes our lives easier. But in certain situations, when they get out into the wild, they don't disappear. They show up in our water. They show up in our food. They show up in our children. And they have a wide range of potential biological effects. They can potentially induce cancer. There's studies that show that that they increase the risk of cancer. They also can they mimic hormones and impact the way the body actually functions?
Yeah, I'm not sure which forever chemical can do that, but a lot of the things that we consume do mimic our hormones and cause early onset things like puberty or aging or cell growth or things that you really don't want to have happen unregulated in a biological system.
I agree.
So what do we do? Is there a balance? Is there a way of being able to have the convenience that these chemicals provide while minimizing the risks associated with them?
So it's actually, I think, Chris, that's connected to the structure of what they're using. There's a lot of discussion between long chain PFAS and short chain PFAS. So meaning big polymers, macromolecules, and the persistence of longer chain PFAS have been reported widely. There is some indication in the literature recently that short chain PFAS may be more benign, meaning that if they shrink the size of the polymer but pack the network more densely, right, you may actually have less of an effect. Hasn't been proven out. There's a lot not been thoroughly studied, but there's a whole discussion of shifting from long to short chain.
So when you
molecules.
say benign, you mean less biological impact?
Yes, is what's being reported. But it hasn't been thoroughly studied and it's out there now.
I think with all of these things, people have no idea what the long-term side effects are. That's why they become commonly used. Now every water bottle is BPA free and all those things. So they didn't go in there being like, I'm going to make a BPA-laden water bottle that's going to have health impacts. It's just, until you have those long longitudinal studies, we're not going to know what they do.
But I guess the other challenge is that there's thousands of these individual chemicals, aren't there?
Yes.
And whereas the studies might focus on one or two specific structures, and I was reading just, the past couple of days saying, okay, fine, this particular, I'm just going to call it forever chemical, has been shown to have negative biological impacts, so we're going to use this other forever chemical. And even though there haven't been studies indicating that this one has negative biological impact, it likely does because it's so similar to the other ones.
Yeah. I think I don't want to liken this to drug research, but I think a lot of the focus in the material science arena and polymer arena now is to somehow build these structure activity data sets where they can study subsets of these things and then make predictive models that will be able to impart on set effects, right? They do that a lot in the drug industry, right? They build these models and they create these surrogates. The derivatization of these things may alter the backbone, may alter the polymer length, but the reality is that hopefully we can study, or they can study enough about the degradation processes or the implementation in order to kind of derive towards more benign, and still keep the convenience but reduce the hazardous effect.
Do you think maybe a better approach is just to try to get away from forever chemicals?
I think I do agree with that. I think there's a whole class of biomimicry that's going on now. So biomimetic chemistry, biomimetic polymers, where you can use things that still give you the hydrophobicity or the thermal capacity that you need, but mimic things that are naturally abundant. You see a lot of work in the cellulose arena. You see a lot of work in other arenas like that.
But I can tell you that that non-stick frying pan in my kitchen, man, I want to keep that.
Well, it already is there, so it's already forever adding to.
and so maybe that's actually an interesting way to go. Where to go next is it's already there, and so are all these chemicals in the environment. They're in the water. It's in the soil. What do we do about that? I mean, we're talking about what we're going to do as a society moving forward from a manufacturing perspective, a virgin manufacturing perspective. But the reality is these chemicals are already in the environment. Is there something we can do to reduce the potential harm associated with that?
Or get rid of them?
I mean, I think your forever frying pan will always be in your kitchen. But the reality is the remediation processes are where people can focus as well, right? So there is a significant amount of work being done on innovative ways to capture PFAS, remediate PFAS, and all these forever chemicals to get them out of the environment. And I think that is a massively strong push in the research arena. A lot of great work being done across the globe on that stuff.
Are you either of you aware of an analogy, an analog, similar situation that happened in the past? I think that, I don't know, Agent Orange and dioxins and things, chemicals that were ubiquitous, or even, I'm trying to think, what was that stuff they used for insulation?
The blow foam.
Asbestos.
Right?
Asbestos. Yeah, I was searching for that. Yeah.
So this isn't new. I mean, this type of a situation has happened in our society again and again. Are we ever going to get smart enough to avoid these things?
So my my perspective on that is it takes strategic thinking and design on the upfront, with not only the scientific vein in mind. I think it's really important to also have the environmental impact, the community impact, and more of the touch factors that are beyond just the science when you're designing an overall platform for product or invention, right? And I think that's super important. And I think if organizations and scientists work together with folks that understand community needs and things like that, you can design a holistic solution that gives you a better platform to work from. But again, it's also a balance of convenience versus platform development and return on investment.
So what I'm hearing you say is that chemists are trying to kill people.
I'm clearly not going to say that. I'm pretty sure that's not what I said.
I thought that was what the physicists
Yeah, I know. Yeah. That's what I'm learning through this podcast is that all the other sciences are evil.
To the American Chemical Society, I am not promoting that chemists are trying to do any of that.
I am not either. I'm teasing.
Just kidding.
Yeah. Don't worry, we'll read the disclaimer at the end.
What else do you want our listeners to know about forever chemicals?
I think twofold. They're here. There's over 4,000 compounds in the classes. They're been used, are being used, but there are regulatory things that are starting to begin to pull back on these things. But moreover, I think I really think giving a shout out to the community that is working on this stuff and the innovative approaches to solve this problem, I think is really going to be the way of the future. I think we have to stop it. Knowing that it's here, we have to stop it where it's at instead of redesigning everything. I think people would lose the convenience aspect, and that would be a different societal impact versus trying to stop it where it's at. So I think point of use remediation is going to be the way of the future, and I think there's a lot of great people working on those things now. So stay tuned for all those amazing inventions that are coming out, I think.
Yeah, and I guess then if we can get rid of them and make them not forever chemicals, then we could still use them. So as long as we can get rid of them and maybe have a way to get them out of the body as well.
Call them for now chemicals.
For now chemicals, yeah.
Better life through chemistry.
Better life through chemistry.
All right. So the views, thoughts, and opinions expressed are the speaker's own and do not represent the views, thoughts, and opinions of Lewis University. The material and information presented here is for general information purposes only, such as chemists are trying to kill people. No, I'm kidding. Okay, the Lewis University name and all forms and abbreviations are the property of its owner, and its use does not imply endorsement of or opposition to any specific organization, product, or service. This podcast was produced in the WLRA podcast studios at Lewis University. Visit lewisu.edu for more information about Lewis University. You've been listening to Science Coast with Mallory Havens.
And Chris White.
And
Jason Keleher.
thanks. Bye.
See y'all next time.